Welcome back. Having seen, many variants of, trade-off between, regularization, overfitting, underfitting, right? Let's now, talk about something, very exquisite, which is otherwise known as, VC dimensions, or actually shattering things to VC dimensions. Okay. So, what really happens is, there is this, if you really have complex data to fit, right, you try to have a more representational power in your fitting algorithm, right, and sometimes you try to do a really good job while fitting the training data, and what you observe is, if you have done a lot in trying to accommodate every tiny weeny point. We have seen this in locally weighted regression also, right? So, you cannot really, if you can't do it on the whole data set, do it in the neighborhoods so that you don't overfit, right? So, you fit well locally, okay? Generally, globally speaking, you really don't, care much, because if your local fits are good enough, the cumulative aggregate of the fit will be good enough, right? So, that's one of the ways to, tackle overfitting, okay, or underfitting, right? And regressions have this problem. Not only regressions, please also know that, it's not only about regression. Everything else. Every machine learning algorithm has this problem, right? So, there is a hard decision to make between the complexity of the learner and the representational power. Okay. So, different learners have different powers. Okay. So, like for example, if I choose this particular learner, which is nothing but, you take the signature of your input data sets, your input features are this, right? So, you take a inner product of the input features and then the difference with the bias, right? And take the sign of it. And if the sign is positive, you label it as one class, and if the sign is negative, you label it as the other class. Okay, simple enough, right? Your predicted classes are CX. Okay, so these are the class predictions, +1 and -1, let's say. Okay, inside the sphere, outside the sphere. Okay, now, so there is this linear classifier, where basically what you do is you have two features, x1 and x2. So you write sort of a line segment, right? And then you claim that this line segment, based on the signature of this line segment, you would classify data points as positive or negative. Okay, all right. So this is simple in implementation, but it has its own problems, right? Because if the data is not linearly separable, what are you going to do? On the contrary, this particular learner actually accommodates the fact that data may be linearly separable, right? Okay, so there are other methods as well. Sometimes, in order to accommodate new training data, you may have to align the line. So basically what you do is you shift the line. The previous model, the line was actually passing through the origin, right? Which means this particular guy has no bias, right? It just passes through the origin with a slope. But if you have more data coming towards you in such a way that you have to incorporate some amount of bias, then that's it, right? And then your theta naught is that bias amount. Okay, all right. So so the usual trade-off. But the question is, once again, as we have seen in regularization and soft margin in SVM, right? You really do not try to manipulate your separating hyperplanes too much in order to accommodate new data points, right? You will probably try to do a soft margin regularization thing. So more powerful learners, it might overfit, right? Less powerful learners may not be able to classify well. Okay, so the question is, how do we quantify representational power? So one solution was proposed by Vapnik, okay, and Vapnik and Chervonekus dimension, or VC dimension, and this is what it is. So what they said was that, look, we assume that our training data are identical and independent and identically distributed from some distribution, right? Okay, and define two things: risk and empirical risk. Okay, so this is nothing but long-term test error and observed training error. Okay, so the long-term test error is basically the expectation of your delta function that it does not fit the class predicted, the classifier well, and the empirical one is just the training error. Okay, basically the training error, that your one training instance does not fit into the predicted class. Okay, so how are these two things related? It entirely depends on overfitting, okay? Because the test error here, the test error could be much worse, right? It's much worse than, the training error, right? So the idea is, given some classifier, and let's say the classifier has some VC dimension, right? With a high probability 1 minus sigma, 1 minus zeta, Vapnik showed that the test error, okay, is bounded by training error plus some constant, and this constant depends upon the VC dimension of the classifier, okay, as you can see, okay, all right. So where n is the number of training examples, h is the VC dimension, right, okay, and nu is the probability, okay, all right. So probability of misclassification, right, okay, and so this 1 minus this is the probability of, correct classification, right, okay. So the idea is shattering. So we say that a classifier, if efficiently designed, can shatter as many points as possible, okay, and achieve a zero error on the training data, okay. So the thing is, if the first classifier, if you recall, can this shatter these 2 points, okay, all right. This classifier, the one with the bias, shattered these 2 points, okay. So there are some possible training sets. So yes, at least what you can see is you change the bias around, right? You change the value of the theta naught, it can shatter these points. You can change this in this direction, it can shatter, right? You change the bias down, you shift the line down, or you shift the line to the other side, right? Okay. So there are, 4 possible training sets, correct? So what happens is, if on the other hand, if I have this particular classifier, can they shatter this? Okay, here I can see no, right? Because the training sets, we said there are 4 possible training sets, right? It can shatter this, it is not able to shatter this, it's not able to shatter this, right? So the answer is no, okay. So the VC dimension, so what exactly, how do we define a VC dimension? It is defined as the maximum number of points that can be arranged so that the classifier can shatter them. So what is the VC dimension of this particular classifier? Let's see. Okay, the VC dimension is 1 because it can arrange 1 point, cannot arrange 2. Previous example was a more generic example, right? So you can have 2 points which are labeled to 2 different classes but can be inside the circle, right? So this is the problem, right? This cannot guarantee that this will not happen, right? But it can guarantee that at least 1 can be arranged, okay. So the VC dimension of this guy is 1. What about the VC dimension of this guy? The VC dimension of this guy is 3 because it can actually take care of shattering 3 points, right? But it cannot do 4, right? So you can have, if you have 4 points, nope, the answer is no, because you can have these 2 points. Remember the XOR example in neural networks, right? So no, so it cannot do that, right? So the VC dimension could be greater than or equal to 3, but it cannot be greater than or equal to 4. Okay, all right. So basically, it's kind of, in order to determine the VC dimensions, there are lots of work that are actually required, and some of the things are pretty complex in nature. So like for example, there is a log likelihood of training data on the number of parameters. There's a Bayesian information criterion, right? Okay, and so probably true Bayesian methods are probably more have more representational power and have greater VC dimensions because they really don't care about linear or nonlinear boundaries. Okay, so these are the problems that primarily you will have classifiers with lower VC dimensions, which are based mostly on the geometric distribution of data. Okay, all right. Having said that, I think so it's just a, what you are expected as in a introductory machine learning course is to realize and understand the VC dimension of some of the classifiers that you have already designed, like for example the regression classifier and support vector machine and stuff like that. Okay, and not to get into more details of how complex the VC dimension is and how are you going to compute the error bound between the test error and the train error. Okay, all right. So that's about it for now. and we'll come back with some of the other classifiers.